There are times when it's easier to find the complement of a set than to find the set itself, and keep in mind that the complement means it's the stuff outside of the set. Sometimes the set itself is really complicated, but the things outside are not complicated. So this is the reason why we need something called the difference rule. Okay, so the rule is if you want the size of A minus B, and B is a subset of A, then all you got to do is count the elements of A and then take away the elements of B. So let me give you an example with some actual numbers. Suppose the set A was 1, 2, 3, 4, 5, and the set B was 1, 3. First of all, notice how the set B is a subset of the set A. So it's part of it, basically. Some of the elements here show up in the A. As a matter of fact, all of them do. Now, what is, first of all, A minus B? What does that even mean? Before we calculate the cardinality, which is the absolute value, what is A minus B itself? What is that set going to be? So remember, A minus B is pretty much all the elements of A that are not already in B. The 1 is already in B, so we forget about it. The 2 is new. The 3 is already in B, so forget about it. And then 4 and then 5 are not in B, so they count. So how many numbers did I just write down? I just wrote 3 of these. So the cardinality of A minus B, in other terms, the absolute value of A minus B, is gonna be 3, because there are 3 elements inside of that set. 3 because of 1, 2, and 3. So that's how we use the difference rule. But in practice, the sets that we're going to be counting are going to be huge. This is the reason why we have to do the difference rule. Sometimes it's very difficult to tell what B is, but we can tell what is not inside of B, the 2, 4, 5, for example, or vice versa. Okay, so let's take a look at example 3, which says, suppose that a pin, and in this case, the pin is a sequence of 4 symbols chosen from the 26 letters of the alphabet and the 10 digits. So we had the same scenario show up in section 9.2. So the question here is how many pins with repeats in their symbols are there? So like, for example, there are 4 digits or 4 symbols. You can have pins like this, A, and then 1. You can have pins like this, A, B, B, B again. You can have pins like 1, 1, 3, 3. So your letters could be repeating, your digits could be repeating. We don't know how many times each repeat is happening. So if we want to count all the combos that have A repeating multiple times, and then all the combos that have B repeating multiple times, it's going to take forever. So instead of counting the set itself, what we're going to do is we're going to figure out the complement of the set, and then kind of take out the complement to get the total. So I'm going to start with how many total pins there are in the universe. Okay, this is with and without repeats. And since the 26 letters of the alphabet are allowed and the 10 digits, the total number of pins is going to be 36 times 36 times 36, 4 times in a row. That's because there are 4 symbols in my pin, and I'm allowing repeats at this point in time. Okay, now let's figure out how many pins have no repeats. Okay, so the number of pins without repeats. Now, to be considered a pin without repeat, you can have anything you want in the first symbol. The second symbol cannot be the first one, so you now have 35 left. The third symbol cannot be any of the previous 2, so now you have 34 left. And the same thing is true for the last pin, which means that that guy is going to have 33 possible choices. So let's put that in a calculator, and that's roughly speaking 230,000. Okay, so now what remains is to think of the set that I wanted. Okay, in order to do that, I'm going to draw a Venn diagram. So this is the universe of all the pins in the world. Okay, so this is every pin that could have ever existed. Inside of that set, there are 2 sections basically. There is one section with pins that have repeats, and there's another section where pins have no repeats. Okay, so I'm going to put on one side pins without repeats, and on the other section I'm going to put the pins with repeats. Now, originally the question said how many pins with the repeat symbols are there. So they want the answer to this guy right here. Okay, that's what they want. I discovered that the whole box has 36 to the power of 4 pins, and I've discovered that the number of pins without repeats is roughly 230,000. So the question is, how many pins are there in the leftover? Well, since the pins with the repeats is a subset of the bigger set, then the number here should be 36 to the power of 4 minus the 23,506.20. So let's put that in a calculator and estimate the value. Roughly speaking, it's 1.5 million pins. These are pins with the repeats. So as you can see, that number is really huge. It was easier for me to calculate how many pins have no repeats, and we've done that previously, so it's kind of straightforward. And then subtract to get the difference, which is the amount that we're looking for. So the answer to the question is that number 1,443,996 pins. Let's keep going to part 2. Now, what if the probability of choosing a pin that has a repeat? So probability of chosen pin having repeat, chosen pin with repeat. Well, again, the answer is pretty straightforward. It's how many pins have some sort of repeat, which is that number that we just got, divided by the total number of pins in the universe. And again, I'm going to do a decimal, then I'm going to turn it into percentage with 2 decimal places. So the answer is 85.98%. Okay. Now there's another way of getting this number right here if you wanted to. Since I already know how many pins have no repeats, I could get this answer by doing this. I could do 1, because that's the probability of choosing a pin, minus the probability of choosing a pin without repeats, which is 235,620 divided by 36 to the power 4. If you do that, that would be using the second strategy that I'm describing over here in this box. So to calculate the probability of a complement, it's the same thing as doing 1 minus the probability of A. So in this case, the probability of choosing a pin without repeats is the same thing as choosing 1 minus choosing a pin with repeat. Okay, and if you plug it in your calculator, you'll find out that this is the same amount. So, that's just another way of doing the problem in case you ever want